Okay, the second part of today's lesson is looking at what we call the law of radioactive decay. So let's think about it, okay? Let's imagine we've a box here with 500 nuclei. And we have another box here with 100 nuclei. And let's say that in the box of 500 nuclei, 10 decay every second. So 10 decay per second. Now, the number of decays per second is called the activity definition, and 1 decay per second we define it as the becquerel, named after Henri Becquerel, French physicist who discovered radioactivity. So that's 10 becquerel. Now, what do you think? 10 out of 500, how many do you think out of 100? Normally someone will give me an answer. And yes, insert name there, you're correct. It will be a fifth, so it will be 2 decays per second. You would expect, okay, because there's 5 times as few, so you'd expect 5 times as few decays per second. Obvious, hopefully. Okay, so 2 becquerels. And that's the law of radioactive decay. That's it. Okay, what it basically says is the activity, this is the activity, and this is the number of nuclei. And basically the law of radioactive decay says the activity is proportional to the number of nuclei. In other words, if you have 20 times more nuclei, you have 20 times the activity, and so on. That's it. Now, if we have a proportionality we've looked at before, it's equal to a constant. And the constant is given the Greek symbol lambda, and it's called the decay constant. Right? Now the minus goes in because it's a decay, because the number is going down. Don't worry about the minus. What does lambda mean? What does the decay constant means? Well, all it means is the fraction of the decay. So if we put these numbers in, let's have a look. Okay, so if there was 500 nuclei, and we got 10 decays per second. Okay, 10 decays per second. Okay, right, well, 1/50th, okay, would be the decay, would be the decay constant, because that's the fraction of the decay. And would that work for the other one? 2 is 1/50th again of 100. It does. So the decay constant, measured per second, unit per second, is the fraction of decay every second. No more complicated than that. Right? So that's it. So we basically then have this formula. Right? That's the formula. Now, one little extra on it. Right? This idea of half-life. Okay? The half-life is the time it takes for half of the nuclei to decay. So you have 1 million nuclei in there, and the time it takes for 500 of those to decay, 500,000 of those to decay, is called the half-life. So it's the time taken for half of the nuclei to decay. Okay, now just think about that. It has to be related to the decay constant, because the number of the decay, the time taken for half of the decay, will be linked to what fraction decay every second. Now, when you're doing exponential functions in your maths later on, this will all become very clear. Okay, and this is obviously very significant at the moment, because we're talking here about an exponential decay, and with COVID-19 and so on, we're talking about exponential growth. So these exponential functions are hugely significant. Okay, and what we're looking at is a decay. What they're looking at with COVID-19 and we're trying to reduce is the rate of exponential growth. Okay, so in an exponential decay, what we actually get is, if you have your activity here, let's have a look at it, and let's say we've time here. Okay, now let's say the time, we just put in 1, 2, 3, 4, and we keep it as simple as possible. Okay, we'll put in 5. Let's say the half-life is 1 second. Okay, these are in seconds. So after 1 second, okay, half of it will have decayed. Okay, so that's that there. So okay, so that was a full amount. After 1 second, half of it has decayed. After another second, half of that has decayed. So after 2 seconds, we're down to here. And after another second, half of that has decayed. And after another second, half of that has decayed. After another second, half of that has decayed. And it keeps going on. And it'll never actually quite get to zero. Okay, and we draw a lovely curve. Okay. And that's your exponential decay. That's your exponential decay. Right? The opposite of your exponential growth. So we're looking at and fearing at the moment of COVID-19. Right, now, how do you find the half-life from this? Okay, well, you just get to you take any point and you take half its point, half of its activity, you go down here and you find the time for that to happen, and that's the half-life, because it's the time taken for the activity to half, or alternatively the time taken for the number of nuclei to half, which is the same, linked to the same thing if you think about it. Now, so there is a link between decay constant and half-life. When you're doing your limits at max later on, you'll see where the link comes from. We have the formula written in our maths tables and we just slot it in. So if you don't have the decay constant, we have a formula, okay, that the decay constant is the natural log of 2, and the natural log links into exponentials, okay, that's where that comes from. It's a natural log, but on your calculator for the time being, okay, that's 0.693, we leave it as natural log of 2 divided by the half-life. Okay, that's in your tables as well. So that's the extra little bit. So when you're doing this, let's go back to the way we operate these calculations all the time. That's your core formula. This is the one little extra formula that could be handy to you. And once again, only 2 variables. So once you have one, you have the other. We'll do questions on paper now and we'll see how they look. But that's law of radioactive decay.